It's been a while, so let's pull it back together. We started dynamics last week, dynamics and momentum. Wednesday's lesson, because we didn't have class Thursday or Friday. Wednesday's lesson, we looked at Newton's first law, the idea that objects in motion will stay in motion, object rest stays at rest, unless acted on by an unbalanced force. And the lesson before that, we'd gone through a long list of forces, not an exclusive list or an exhaustive list. It is not every force that is ever going to be discussed at any sort of level, but the most common ones and the ones that I have specific lessons for, we largely are on that list. And then we came to back to Newton's law, and we talked about the concept of inertia, the idea that there is a property of objects that resists change to their motion, and how you experience those in various forms of your life. We drew some free body diagrams of objects. We talked about different situations in which inertia plays a role in your life, and then we had, just kind of 6 questions here, because we skipped that one, where we talked about inertia and the effects of inertia, and again, how some of it is wildly counterintuitive to the way you expect things to work, and through no fault of your own have been exposed to a whole bunch of incorrect demonstrations of all of these things. Everyone who has had the misfortune of being wildly into science fiction, like I have been for so much of my life, you'll learn that there are huge parts. Yeah, Matthew will throw you the desk out here. Yeah. There's huge parts of science fiction that do what they do, and then it's all wrong as far as the physics would actually go. Okay, give me a sec while you Massey set up on that's here. Okay, Massey, here you go.
How you gonna dump it, boy? 400. They come in with like $5. $5. Bradley, bro. I don't know. I don't have your number saved. Oh my God, Christine died.
Okay. Where were we? Right. And then there was some kind of there was a few kind of niche real world scenarios that we talked about down here at the bottom. A scenario like this, where you've got a string attached to a heavy object and you're pulling on another string. If you pull the string slowly, we talked about why A would break first. But if you yank really hard, because of the inertia of this stationary large object, because it is resistant to changes in its motion, B is the string that's likely going to break first if you yank on it. Similar in idea to the whole like place settings on a table, and you pull really hard on the tablecloth, the dishes stay on the table, but if you pull really slow, then everything comes off with you. It's the same idea. And then how you put the head back on a hammer, if it's broken, this is the easier way of the two to do it, because here you're driving the handle into the head of the hammer, but here you're allowing the inertia of the head of the hammer to force itself back onto the handle. So just some examples of inertia. I didn't assign this. I'm going to skip this. I've assigned it a few times. We've done it as a class. I don't know that it's altogether that useful. So we're going to skip it for the time being. And we're going to go ahead and we're going to take a look at now specific examples of different forces. And we're going to start with gravity, the one you are arguably the most familiar with. So, gravity as a force. Now, we talked about it in kinematics as something that causes an acceleration. We had you guys try and measure the acceleration due to gravity. I told you that the number associated with gravity was 9.8. And we didn't talk about forces at all. So now we're going to talk about the force of gravity. Because something has to be doing the accelerating. And gravity is an interesting one. You can think of gravity as a force. Newton did. It's kind of the beginnings of a lot of Newton's work in physics after he did all the calculus, was to talk about gravity, and he put together these ideas for gravity. So the force of gravity is a force that pulls down, and I'm going to put down in quotes, because what is down really? If you're here in Canada and you point down, quote unquote down, you're going to point towards the center of the earth. But you go to Australia and you point down, as I heavily air quote that, you're pointing to the center of the earth, but because they're on the bottom of the earth, what's bottom in space? You're actually pointing in opposite directions if you're in the southern hemisphere versus the northern hemisphere. So, I mean, what's down? A force that pulls down, I'll say here, or toward the center of a massive object. And I don't mean massive the way you might think of the concept of massive. When I say massive, you think what? What does the word massive mean to you? Big. I say massive, you think big. When I say massive here, I don't necessarily mean, it doesn't, often they are big. They don't have to be big. A massive object is any object, massive, it has lots of mass. And you can have very, very small objects that have a ton of mass, relatively speaking. For example, I don't know if you did astronomy in Science 10. It's a unit in Science 10. Lots of the times people don't teach it because we don't have time to get to it. An example of a massive object that isn't actually that big is something like a neutron star. A neutron star might be like 20 times the mass of our sun, but you could fit it comfortably in downtown Vancouver. A neutron star would not reach out to Abbotsford. It's not on a solar scale. Neutron star is not very big, but it's going to be multiple tens of times the mass of our sun. So when I say massive, I just mean it has lots of mass. It doesn't have to be very big to do that. It has a lot of mass. What's mass? Now we have to define it. It came up last week a little bit when we were talking about space and the concept of weightlessness. You can be effectively weightless in space, but then Emma brings up the Vomit Comet. You didn't call it that, but that's the name of the plane that you were referencing. There's a 747 that's been repurposed it flies big arcs. And when it drops at the same rate gravity pulls you down, and so the people inside are floating in the plane with the plane as it falls towards the earth. And so it looks like they're in space. It's how they shot huge chunks of the movie Apollo 13. Yeah, you can put your phone in here and grab a calculator. I'll take the iPad for a sec. Well, it's not even on. Is it stuck?
I don't know, I'm just asking, give me the iPad.
But was it on when they gave it to you?
No, it's off.
Is it dead?
It's here.
I think it's dead. You need to get one that works.
That's fine.
If you want, it doesn't turn on. Battery's dead.
That's fine.
So you're not going to translate? Okay, if you need translation, ask me. Okay, so the Vomit Comet, 747 repurposed to mimic what you see. I'm sure you've seen YouTube videos of it. If you watch the movie Apollo 13, it's how they filmed it. They didn't actually go to space for Apollo 13. They went onto this aircraft. It goes up, you feel very heavy, and then the path that it follows, it just starts to fall, which is not usually what you want a plane to do. And then everyone inside just falls with the plane. So as far as it looks to you, you're just weightless, bouncing around on the inside of the plane until the plane hits the bottom of the arc, and then everyone falls to the bottom. But that's what weightlessness actually is. If you've ever been in free fall for any length of time, hands up if you've ever been cliff jumping, hands up if you've ever been bungee jumping, skydiving, what else? You fell off a roof. Like any of these, so that is what the feeling you felt, that kind of awful stomach lurching feeling, is the feeling of weightlessness. Weightlessness just means you're in free fall. So you're never massless, which brings us back to the other inertia question I asked you the other day. If you're floating in space, weightless, with an elephant and a mouse, and the elephant hits you and the mouse hits you, which one's going to have the bigger impact? Even though all three of you are weightless, the one that's going to impact you is the one that is the most massive, and so that's going to be the elephant. The elephant is going to have the largest, the more massive you are, the more inertia you have, and so the more inertia you have to transfer, so the more massive thing is going to be the elephant. You are not massless in space, but you are weightless. So those concepts must be different. What's mass? That's volume. It's related. The amount of space you take up is volume. Density is how much is packed into the space you take up. What did I tell you was not the case? Weight, they're related, but they're not the same thing. If you take what you said, Kai, and you take what Emma said, and you put them together, you're going to get the definition. You're going to get a definition for mass. You said density is how much stuff is packed in to the volume, which is the amount of space you take up. Mass is the other piece to that. It's the stuff itself. Mass is the total amount of physical matter in an object. And an important piece to this is constant everywhere. If you know your mass in kilograms, let's say you're me. I'm about 100, I'm a nice easy number, about 100 kilos. Those of you who think in pounds, it's about 220, 222, 225, something like that. 100 kilos. You take me from the Earth, you put me on the moon. My weight will change, my mass is still 100 kilos. You take me to Jupiter, my weight will change, my mass is still 100 kilos. You take me out into space, away from absolutely everything. I am now weightless, but my mass is still 100 kilos. If I want that to change, there's a few ways you can do that. You want more mass? Depending on the kinds of physical matter you want, you can sit there and eat more. Or you can go to the gym and pump weights. The mass you're getting is different. One is muscle, one is fat. If you want to lose these things, you can either just sit and do nothing, and you will atrophy. If you want to change your mass quickly, you have to start cutting things off of you. That is how mass changes. But if we just port you around the universe, your mass will remain the same. Your weight, though, your weight changes. Weight is defined as the interaction of gravity with your mass. And it's complicated a little bit. Well, it's slightly more complicated than we expect it to be. Memphis. Yes, thank you, sir. Unfortunately, you missed ice cream this morning. Next time, come to class first, because I would have had you make the ice cream, and then I would have sent you to finish this thing.
Oh, okay.
So, next time. But thank you for finishing that for me. Okay, Weight is the interaction of gravity with your mass. But if you are falling in a gravity field, so on Earth, you don't feel the gravity. You feel the sensation of falling, and that's what weightlessness would feel like. So you need to have a weight, a measurable weight, an experiential weight. You need to have an interaction of gravity with your mass while you are what? If you can't be falling, you guys experience, you can feel your weight right now. If you lifted your arm up and down repeatedly here for a while, it would get tired because you're exerting yourself. There's mass here in my arm. Well, there's a balanced normal force. When you fall with gravity, you don't experience your weight. It's when you stop at the bottom or you're just sitting here. You're stationary, and now you have to get up. You're going to jump here for me in a moment. You guys are going to do some jumping. And you're going to experience your weight, at least on the way up. You'll experience brief weightlessness on the way down. Mass is constant throughout the universe. Weight changes depending on where you are. Because if weight requires the interaction of gravity, and gravity is created by a massive object, as soon as you change the massive object, you're going to change the experience you have of gravity. The formula for the force of gravity is very simple. It's this. The force of gravity is equal to your mass, little m, times little g. And I will define those letters for you here now. M is the mass of the object, whatever it is. Little g, which I will teach you how to calculate, is the gravitational field strength. That is the definition of little g. We've already talked about it with a different name. So gravitational field strength is the same as talking about the acceleration due to gravity. And we know this value on or near Earth is 9.81 newtons per kilogram, or meters per second squared. These units now mean the same thing. On or near, that's an or, on or near Earth. And this number isn't actually, this is a rough number, because there are places you can go to on Earth where this number changes. Depends on the density of the ground underneath you, depends on how far away you are from the center of the Earth. This number is lower at the equator. It's higher at the North and South Pole. It's lower in Denver, of all places. This number changes depending where you are on the globe, but this is a good enough average number. Stop me as you're going if we got questions. This is the formula for the force of gravity, dependent on the mass of the object experiencing gravity, and it depends on the gravitational field strength that causes the acceleration of gravity. So G varies depending on the mass of the object, creating gravity, and how close you are to that object. Because any object with mass will produce a gravitational field. You guys are actively, and we'll look at how do we calculate it, and then you'll figure out why you can't actually really feel it. But you guys, because you have mass, you create a gravitational field. There's all sorts of physics pickup lines related to that idea. No, because there's so many other things that dominate the teeny tiny field you produce. But if you were out in space away from everything else, and that speck of dust was out there in space with you away from everything else, it would, yes, it would orbit you. It could be made to orbit you, because you would be the only source of gravity out there. So, examples on Earth at sea level, G is 9.81 meters per second squared. On the moon, that number is smaller. It's 1.6 meters per second squared, much smaller. So if you've ever seen footage of guys jumping on the moon, they don't jump like we do here on Earth. They fall a lot slower. On Jupiter, Jupiter has a value of 24.5 meters per second squared. On the sun, that value is much larger. That value is 275 meters per second squared. The acceleration due to gravity on the surface of the sun is very, very, very large. I have a video that helps demonstrate what this looks like. Okay, where is that? It's this video right here. No. Pause you. Thank you. Here we go. And my daughter is adorable. It's true. Okay, so I don't know why it looks this way, but it does. Here it is. So there's a car here, and different things are going to fall on the car. Maybe if I zoom this in, will it look different? No, it won't look any different. Different things are going to fall on the car under the experience of different gravities. Here we go. So Mars is similar in size to the moon. If you've studied astronomy, Mars and our moon are almost the same size. So their effective gravity is going to be very, very close. There's the moon, a little bigger than Mars. Pluto's not a planet. Very slow. So I heard the comments about when I said this number, some of you are making comments that you might not even be able to stand. As soon as the car was on the sun, what happened? Yeah, the axles, something snapped, the car dropped, and now this is all that is. There was no bounce there. And so these real world, well, relatively speaking, as far as simulations go, approximation of what it would look like to be under the effect of those different gravities. Yes?
What decides, or what influences, gravity on each planet? What about the sun? Why does the sun have so much gravity than, some other planets that have, barely any?
G varies depending on the mass of the object creating the gravity.
Oh, it's about mass.
It's all about the mass of the object creating the gravity. So, I mean, I teach this during, were you in my science class? Science 10?
No.
Okay. Okay. So here's I any excuse to get out my popsicle sticks. So here's Jupiter, Brad. You can hold that guy up. If Jupiter is this big, so Brad's asking why the disparity in gravity. If Jupiter is that big, and we have to give Earth for context. Read, you can get the Earth. There's the Earth. If the Earth is this big, Jupiter is that big. I made these. I did all the math. This is accurate. The Sun.
Pretty big.
This big.
Oh, okay, so
And it's not two-dimensional. This is two-dimensional, right? So imagine a sphere this big, full of stuff.
What is it full of?
Sorry?
What is it full of?
All sorts of stuff. Right now, our sun is full of helium and hydrogen. I'll see. Now we're going to go here. Take some of my Science 10 astronomy unit. Awesome. But yeah, this is why.
okay.
9.8 meters per second squared, 24.5 meters per second squared, 275 meters per second squared. Just because there's so much stuff packed into these spaces. Iron, molten and solid iron is really where most of it's coming from. Yeah, sire. We work it backwards. We know the effect. We know the effect of the sun on our Earth. We know how far away the two centers are. So because we know how far away they are, we know the mass of our planet because of how it interacts with us. The gravitation, we know the radius of our planet. We know the effect of gravity on objects at the surface of our planet, 9.81 meters per second squared. And so we can work that backwards and figure out the mass of the Earth. Earth has to have a particular mass because it creates a particular gravitational effect at its surface. We know how far the sun is away from our planet. We know what the effect of gravity is on our planet because of the way it orbits. Because of those two pieces, we know how fast our planet is moving. We know the radius of its orbit. We can work backwards and figure out, for this to happen the way it's happening, the sun must have this mass. That's how. Yeah.
Why aren't we just getting closer to the sun?
We will talk about that later. It's the same reason why we can orbit. The moon is going around our planet without slamming into it. It's the same reason why we can orbit our planet without slamming into it with satellites and stuff. We'll talk about that. So, these are all very good questions. We will get there. Okay, so what you're going to do now is we're going to determine your weight a bunch of places. I would like you, if those of you who have driver's licenses, we are going to assume, and this is the hilarious thing, we're going to assume that your driver's license is what your mass actually is. I had a student whose driver's license had a typo. Do you guys remember Reet Dillon from a couple years ago? She had a typo on her driver's license. They added a 1 in front. So she was an extra 100 kilos beyond what she should have been. It was hilarious. But whatever your driver's license says your mass is in kilograms, I want you to get that number out and I want you to write it right here. So mine says I'm 100 kilos. Write that number in here. Whatever your driver's license says your mass is, use that value. If you don't believe it, or you'd like to actually see what your mass is, if anyone would like to hop on a scale, I've got a scale for you. If you'd like a better number. Everyone needs to find their number. What is your mass? Okay, find the number, write it down.
Oh my God.
Find your mass, write it down.
For you.
Nice. Write it down.
What are you at?
Well, Lachlan, a lot of numbers right here. 1 kilogram is 2.2 pounds. So if you need to do the conversion, do the conversion. Okay, so here we go. Your mass is that number in kilograms. If you know it in kilograms, that's a mass, not a weight. So now we've got to convert this thing into what your weight actually is. Because, hey guys, stop talking. You figure out what that is and then keep it to yourself. Because weight is a force, it's the interaction of gravity with your mass. The units of weight are newtons. So my number is really easy. I just take the 9.81 and I multiply by 100. Move the decimal place twice. It's why, as a physics teacher, 220 pounds is a good, I don't know, I'm just making crap up at this point. I'm 220. So my mass is 100 kilograms. Use your numbers for this. My mass is 100. We're going to multiply that by, or if you don't want to use your numbers, fine, use my numbers. Multiply by 9.81. My weight is 981 newtons. Now, I would like you to draw a vertical line down here. And you are going to add the words equivalent earth mass. And we're going to find some fun things. So my mass anywhere in the universe is this value. Yours is your value in kilograms. My weight on Earth is 981 newtons. Let's figure out I want your guys' weights on the moon. So it's the same formula. Weight is the force of gravity. It's equal to m times g. The only difference here, m is going to be the same. The only difference here now is that g is 1.6. On the moon, the gravitational field strength is 1.6. So what is 100, for me, 100 times 1.6 is 160 newtons. Find your number. And then what I want you to do is once you've found your weight on the moon, to give you a perspective of what that actually is like on Earth, I want you to take that number and I want you to divide it by 9.8. So for me, if I divide 160 by 9.8, I'm going to get my equivalent Earth mass. It would be what I would feel like on the moon is the same as me being 16 kilograms on our planet. So for example, I would feel on the moon as if I was as big as I am with my 2-year-old's mass. He's 16 kilos, roughly, about 30 pounds, just over 30 pounds. If I was as big as I am with the mass of my son, that is what it would be, would be my experience of my mass on the moon. Yes. Yes. That's what I wrote here. So multiply it by your mass times 1.6 gives you your weight on the moon. Divide that by 9.8 would give you your equivalent Earth mass. Do the same thing for Jupiter. 100 times 24.5 gives me 2,450 to figure out newtons. To figure out my Earth mass, I'm going to divide that by 9.8, and that would be 250 kilograms. That's equivalent to me at my size being just right around 600 pounds. So 3 of me packed into the space of 1 of me. Be an interesting kind of mental exercise to experience. And then I want you to do the same thing with the sun. Fg is 100 times 275 is 27,500. My equivalent Earth mass would be 2,800 kilograms. Just to put that into perspective, this, to give you guys perspective, this is the largest known mass of the black rhinoceros. My experience of my mass, as you see me in front of you, if I went to the sun, it would be, I would experience myself weighing the same amount as the largest ever black rhino. Rhinos are not small creatures if you've ever been to the zoo. Yes. Your muscles are holding the weight. The weight is the mass of the object you're lifting, coupled with the gravity where you are. So no. If your muscles are designed to lift a particular mass here, and you went to Jupiter, that's the whole point of the exercise. The moon, yeah. My muscles, the way I am built right now, are designed to help me comfortably operate 981 newtons of weight. On the moon, or sorry, about 100 kilos of mass. On the moon, I'm 16 kilos. I'd be flying all over the place with my muscles the way they are optimized right now. So the moon, I'd be bouncing all over because my mass is the same as if I was 16 kilograms on the Earth with my same muscle strength. Oh yeah. And you would jump way higher, which is the lab we're going to do right now. You guys, yes, you could toss things on the moon that you could never toss here on Earth. Yeah, like a car. Absolutely. So what kind of car do you drive, Emma? Who here has, hands up if you have your own car? Henry, what do you drive? A Kia what? Kia Sorento. Okay. So the mass of that the mass of that Kia Sorento, the curb weight of Henry's Kia is about 2,000 kilograms. So 2,000 kilograms times 1.6 divided by 9.8. So Emma, if you could lift, I just did the exact same calculations here, but with Henry's Kia. If you can lift, anyone who could lift 326.5 kilos, so that's 720 pounds. If you could lift a 720 pound weight here on Earth, you could toss Henry's car into the atmosphere on the moon. That would be the equivalent exchange. If you can lift 720 pounds, you could lift Henry's car on the moon. This is the calculation you'd have to do. Who can bench what they would consider to be an impressive number? Henry, what can you bench? You can bench 210? Can anyone knows you can bench more than 210? Jaden, what are you benching? 225? Okay. So 2 plates on either side is 45, is 180 in the bar? No, 45. No, it's 40. What? The bar itself is 45? Bar 45. Okay, so that's 5 45s. Yeah. Okay. That's impressive. So Henry's car would be 3 times that. What Jaden is currently benching, Henry's car on the moon would be 3 times that. Okay, so here's what you're going to do. You guys are going to figure out what your vertical would be on the moon and on the sun. Here's how you're going to do it. To determine the purpose of this little activity is to determine how high you could jump on the surface of the moon and the sun. You are going to do this in partners or in groups of 3. You're going to have your lab partner measure your best vertical on Earth. Now, the easiest way to do this is the stupidest possible way to jump. Because we don't have that fancy thing they do in the gym, where you have the bar with the little flappers at different heights, and you crouch and you jump and you slap the thing like they do at the NFL Combine. We don't have one of those. And so the easiest way for us to measure your guys' verticals is to measure you from the ground to as high as your feet go. Yes, Brad, you need a hand up?
Do we have both have to jump, or is it just one?
Everyone's doing this activity. All of you are going to find your verticals. My current best ever as a high school physics teacher, the best number I've ever seen was Nick Martino 2 years ago. So do you guys remember Nick Martino? His was the best number I've ever seen. Finish your question. I think I've got it written down on my old notes. Thank you. I can find it for you. I think I've got it. Nick Martino's the best number I've ever seen. So let's see, and I think I've got it written down, so let's see what you can do. Yeah, take your time. So you're going to jump, and I will demonstrate how awkward this jump is. Yup, it's a straight leg jump. So be careful on the way back down. You want to loosen yourself on the way back down, otherwise if you land, lock knee, it could really, really hurt. Don't do this.
Probably just measure the distance between your full on.
So what you're going to do, you're going to jump, and you're going to keep your legs totally straight, because then everyone is the same. And you're going to measure, your partner is going to try and see, or you're going to film this, students film this to make their life easier. You're going to put the meter stick up against the wall, and you're going to measure your straight leg vertical. It's going to feel stupid, it's going to look stupid, but everyone's on the same page. We're all going to look stupid together. That's how you're going to jump. We're going to measure these values. You can film it and look at it in slow-mo to see, but you've got to get down to that level so there's no like parallax, like you're not looking at it at an angle. You're all going to be at the level. You're all going to do this. I'm going to make some space around the walls, and we're going to figure out what your vertical is. Once you've done this, and you're going to all look as stupid as I just did, and it's going to be great. You're going to determine the initial velocity of your jump. You're going to determine the VI with which you left the ground. Because, and that's easy to do, because we've done it all already. How are you going to find VI, we need some information. We need what? VF equals frickin' 0. We love that. Why is it 0? Because you're measuring yourself from the ground to the top. And at the top, you stop. So VF is 0. Love that. You're going to measure this value. This is measured. What other piece of information do we have? Where are we all jumping? We know the acceleration is what? Almost negative. Because you're being accelerated down towards the ground. So what this VI is, it's after you've pushed off as straight, when you've reached straight leg, you have an initial upward velocity, that's what this value is going to be. You're going to find that. You're going to measure your vertical, you're going to find your initial velocity. Now this is where we're going to have to suspend our belief here. We're going to assume that you will be able to attain the same initial velocity on the moon and on the sun. This is obviously not true. On the moon, you'll go faster. On the sun, you'll go slower. But let's assume because we can't do anything else, that VI is going to be the same for your jumps on the moon and the sun. You're going to do this again, except now you know this VI. This VI is the same. VF is still 0. You're going to calculate D, and this value changes depending on where you are. On the moon, it's 1.6, negative 1.6. On the sun, it's negative 275. This are those two parts, moon and sun. Questions, comments, concerns on what we're doing? Okay? And then by the end of the class, you should all have numbers. You don't need your mass for this, because your mass doesn't matter. So if you haven't weighed yourself, don't worry about it. But you are going to all have to weigh yourself in a little bit when we talk about where to measure your horsepower in a couple weeks. How many horses are you? Not mass-wise, but like power. How powerful are you? So we'll measure you again later. This is what you're doing. My meter sticks are all right here. If you would like to tape them to the wall so you don't have to worry about holding them, my tape is over here as well. You have your task on your mark and set go. In groups of 2 or 3, measure your verticals. Yes.
What's up? He wants me to weigh myself.
No. He will.
I don't need to show you my weight.
Don't worry about it.
No. 75.
You got 20 minutes. Let's get going. Get a meter stick. Start jumping. Tape's on the table. Yep. If you're in a partner, you should absolutely have tape. Get some tape to tape to the wall.
I know you can touch hard, but you're also a lot. You're also hard. Yeah, you know? Oh. Yeah, take the spiral. If I lose, it's because I'm in a
Oh, yeah.
Centimeters, guys, centimeters. Centimeters, not inches. Everything, and technically you're going to convert centimeters to meters. No inches. Inches are bad.
I go first? No, you got first. How many attempts are you supposed to get?
If you want to practice a couple times first, go for it. Whatever your best vertical, using this awkward jump method.
We gotta
make sure the stick is straight up and down.
You probably just put the camera on the ground and record it. No, but then it's on a down angle.
You don't want it angled. It's gotta be level.
Yeah, okay. You go back up. What are you gonna hit me?
See if I have Nick's numbers. Do I have Nick's numbers?
Wait.
Where's Nick Martinez? Oh, I totally don't.
I can't even read the. Okay, you go first. I'll show you how to. No.